Okay, in this video, we're starting our review for the Q4 test, and our objectives today are to find all roots of each function by using graphs, synthetic division, and or the quadratic formula. So, I've got several examples that I'd like for you to complete today. I'm going to work through 9, 11, and 15 from this set, and I'd like for you to complete the rest on your own. During the second quarter of this class, we made it abundantly clear that the quadratic formula is a technique that's perfect for quadratic functions. This will always give us a pair of results that we can use, both real and imaginary, but none of these examples are quadratic formulas. So we've kind of graduated out of quadratic functions, I should say. But it is possible to reduce these in size from third degree and fourth degree polynomials down to quadratics. And when we get there, it might be beneficial for us to use the quadratic formula. We also said during the second quarter that using a graph is a great way to find a solution or pair of solutions. Anywhere that the graph touches or crosses the x-axis, we have identified a solution. Now, the only trouble here is that using a graph only produces real number solutions. So graphs produce real numbers only. So if it doesn't produce all of our roots, and our objective again was to find all roots, if it doesn't produce all roots by using a graph, then we're going to have to use synthetic division and quadratic formula perhaps to supplement. So let's start with number 9 here. I went ahead and graphed a bunch of these using Desmos, and I captured the image just so that you can see this, so that I'm not switching back and forth between my graphs screen and my notebook paper here. So I would encourage you to graph this equation on your own set of, or on your own Desmos page. This is the function, and I don't recall exactly what it was. I'll pull it up in just a second. But the equation is a quartic equation. X to the 4th power minus 5x squared plus 4. X to the 4th power minus 5x squared plus 4. So because this is a quartic equation, then I know that we should find 4 solutions. There has to be 4 solutions. And then fortunately for us, 1, 2, 3, 4, all 4 of them present themselves right on the x-axis. So by using the graph only, we should be able to find all 4 of these solutions. Here's one at -2, another one at -1, another at +1, and +2. And there you have it. We're done. We found all 4 solutions. And what's really nice about this is that they are exact solutions. There are no decimals or fractions are okay, but there are no decimals to throw us off or anything like that. These are nice integer value solutions, and I'd be happy to see those as final results. Question 11, on the other hand, produces this shape. And let me double check what that equation was. Okay, so that one was x to the 4th power minus 81. Well, again, we're dealing with a quartic equation or a quartic function, so there needs to be 4 solutions. Now, 2 of them present themselves very nicely. 2 real number solutions exist here at -3 and +3, but we've got to find the other 2 as well. And it looks like those are going to be imaginary number solutions. So to do this, I'm going to use synthetic division because we already have 2 solutions that are known, and I can use those known solutions to reduce this polynomial from a 4th degree down to a 2nd degree. I can factor out 2 of these solutions and get it down to a quadratic. So here's what I'll do to set this problem up. I'll build my L chart like we have used for synthetic division problems in the past, and I'll write the number 1 that represents 1x to the 4th, 0 for 0x cubed, 0x squared, 0x, and -81. So this set of numbers represents the coefficients for this particular polynomial. We had several terms missing in the center here, namely x cubed, x squared, and x to the first power, and that's why we've got these zeros as a placeholder. Now, -3 was a solution to this, so I'm going to use -3 as part of my synthetic division process, and I'm going to begin that process. I always start with a 0, and that kind of primes the pump, if you will. 1 plus 0 is 1, and the rest of the process requires us to multiply this number on the outside times the result of each column. So -3 times 1 is -3. 0 plus -3, or 0 minus 3, is again -3. -3 times -3 is +9. 0 plus 9 is 9. -3 times 9 is -27. 0 minus 27 is -27. And finally, -3 times -27 is 81. You can check that with a calculator if you need to. This leads us to a nice result because -81 plus 81 is 0, which is what we were after. We wanted a remainder of 0 after we perform the synthetic division. So that just confirms that this was indeed a factor. Well, we knew it was a factor. We knew it was a solution because the picture showed that to us. But the reason why we did the synthetic division is we've now reduced this from a quartic expression to a cubic expression. These four numbers here represent 1x cubed, 3x squared, 9x, and -27. Now that's not good enough because I don't want to, try to find the remaining solutions of a 4-term polynomial. Let's see if we can knock it down a step further by continuing this synthetic division. Now my other answer was a +3, so I'll use +3 with the remaining factors, the remaining coefficients of the synthetic division process. And we'll run through the synthetic division steps again. Start with a 1 plus 0 leaves us with 1. 3 times 1 is 3. Those sum to make 0. 3 times 0 is 0. This makes 9. 3 times 9 is 27. And again, the sum of -27 and +27 is also 0, which indicates a remainder of 0 as well. This again verifies that we have a solution at 3, and that 3 was helping us to factor this polynomial. Now what I'm going to do from here, since I'm running out of room, is I'm going to jump over to this side. This 1, 0, and 9 represents the equation x squared plus 0x plus 9. Now 0 times x is just 0, so we don't need to show that. We have x squared plus 9. And ultimately, to find our remaining solutions, we've got to answer the question, when does this polynomial equal 0? When does x squared plus 9 equal 0? Well, that's easy to solve using square roots. We'll subtract 9 from both sides, and we're left with x squared equals -9. I'll just make a note of that here. We subtracted 9 from both sides. And when I have an x squared equals -9, you should have some red flags going off in your head here. X squared can't equal -9. You can't have a number that multiplies by itself to equal a negative result. But if we could, we would find it by using a square root. And x would have to be the square root of -9, both in its positive and negative form. But you should recall also from the very first quarter of this class that we can take the square root of a negative number if we factor out the letter I for imaginary component. So the solution for x is both a positive and negative I times the square root of 9. And the square root of 9 is 3. So we'll call this positive and negative I times 3. More typically, we'll write it in this fashion, positive and negative 3i. So if our job was to find all solutions to this particular equation here, well, the solutions from the graph were -3 and +3, but the solutions using our square roots method and potentially the quadratic formula, if you had gone that path, after synthetic division, that is, would be 3i and -3i. And now we have all 4 solutions that we were after, 1, 2, 3, and 4. We started with a graph, continued to work with synthetic division, and ultimately finished with the square root property, although the quadratic formula could have worked here if we had said that a was 1, b was 0, and c was a +9. Again, could have used the quadratic formula. For the last example of this video, I'm going to jump down to number 15. And the equation for this graph was f of x equals x cubed minus 18. We should recognize that there will be 3 answers to this problem, and we do see all 3 answers on the graph, so that's a good sign. The trouble that I have with this is that 2 of our solutions, this 4.243 and -4.243, those are decimals here that aren't very precise. We can do better than that. So I think what we'll have to do is either factor or use synthetic division and ultimately end this problem with the quadratic formula to find precise results. Now I recognize a GCF with this problem, so that's what I'm going to do right now is factor using a GCF of x. And again, we should recognize that once we have a polynomial that's factored, we set each of those factors equal to 0. Well, when does this first factor equal 0? Well, that happens when x is 0, and we saw that here with this particular picture. Now the second question becomes, when does x squared minus 18 equal 0? Well, again, we could solve this using the same technique from before and use square roots to find that. But I'm going to go ahead and use the quadratic formula since some of you may not have seen that recently. With this particular example, we have an a value of 1, a b value of 0, and a c value of -18. You should recall that I recommend calculating the discriminant first, which is the result of b squared minus 4 times a times c, b being 0, a is 1, and c is -18. So 0 squared is 0, -4 times 1 is -4, times -18 is +72. So we have a discriminant that's equal to 72. Now I like calculating this first because I've memorized the quadratic formula that provides us the x value as the opposite of b plus and minus the square root of d divided by 2a, where the opposite of 0 plus or minus the square root of 72 divided by 2 times 1. Well, that's easy to simplify. Square root of 72 divided by 2. We can't just divide 72 by 2 here because this 72 is protected by the square root sign. So let's see if we can simplify that using a factor tree. Now I recognize from my times tables that 72 is the result of 9 times 8, which is particularly helpful because 9 has a square root. 8 can be factored into 2 times 4. 4 has a square root, and 2 is prime. So because of this factor tree, I'm going to move a 3 to the outside of the square root sign. Because of this 9, the square root of 9 is 3. I'm going to move a 2 to the outside because the square root of 4 is 2. And I have to leave a 2 on the inside. And so another way that we can think of the square root of 72 is 6 times the square root of 2. Now real quickly, having seen that, I don't know why I didn't notice this first. I'm not on top of my game here. But what if we had saw that 72 is the same as 36 times 2. Well, 36 also has a square root, which is 6. 2 is a prime factor left behind on the inside, and we would have gotten to 6 times the square root of 2 that way as well. Now I've just rewritten the number square root of 72 into 6 times the square root of 2. This is particularly helpful because now I can reduce this fraction. 6 over 2, those two numbers can be divided. I can't divide into the square root symbol because of that, essentially that grouping that protects it. But I can simplify 6 over 2, which equals 3, times the square root of 2. Now in my haste, I forgot to include my plus and negative sign, so I should really include those along the way. And I'm led to believe that my other two solutions as precise answers are 3 times the square root of 2 and negative 3 times the square root of 2. That answer written this way is much preferred instead of writing them as fractions. So I'm going to say that the final solutions here are going to be solutions at 0, at 3 square root of 2, and negative 3 square root of 2. And if you're just not sure that these radicals are correct, you can bring up a calculator and check. Well, 3 times square root of 2 is 4.2426. And there's this decimal, 4.24. Now this is probably rounded, but I think we've got a matching solution. And then the same thing would hold true for negative 3 times the square root of 2. Well, there's negative 4.243 when rounded. Here's negative 4.243. So if precision is what we're after, then this is how we'll get it, using square roots as symbols rather than decimals alone. So I hope this video helps you out. Again, there are 3 completed examples now out of the several that you have to complete. Your job is now to finish 5 on your own. Let's go ahead and call number 17 a bonus. As I look at it right now, can be a little bit challenging here. What I would recommend if you do attempt this is to multiply these together or distribute the binomial into the trinomial over here on the right hand side. Complete that distribution and then look at the polynomial that you have and solve it using the techniques that we practiced in this video. I should see you on Tuesday, so if you have questions for me then, please make sure that you're ready for them. Thanks.